So let's look at the following example that will deal with an object that is in static equilibrium. How much force must a biceps muscle exert when a 10 kilogram mass is held in the hand with the arm stretched outward in the horizontal axis, along the horizontal axis? So let's look at our diagram. Here we have the arm, so we have the bicep muscle attached to this bone, and these two objects point along the y-axis. And this bone is held along the x-axis, so this bone is parallel to the x-axis. Let's suppose that the mass of the object is 10 kilograms as given. The mass of the entire bone, this entire section, minus this mass is 2.2 kilograms. The entire length from the axis of rotation from the joint to where the object is located is 40 centimeters. The center of mass of this entire bone section is exactly at the middle, so it's found 20 centimeters from the axis of rotation, our joint, and from the axis of rotation to where the bicep muscle acts, creates its force, is 7 centimeters. So knowing that information, we want to calculate what the force created by the bicep muscle is or must be so that our entire object is at equilibrium, is at static equilibrium. So let's begin by drawing our force diagram. So we have three forces acting on our object, on the bone. So force number one shown here is the force created by the bicep muscle. So this is the force we're looking for. And the distance from the axis of rotation to force 1 is 0.7 meters. Now, force 2 is the force due to gravity acting on the entire bone section at the center of mass. And the distance from force 2 to the axis of rotation is 0.2 meters. Now finally, force 3 is simply the force due to gravity acting on the object, and force 3 is found a distance of 0.4 meters from the axis of rotation. So we choose upward to be positive and downward to be negative. Notice that force 1 creates a torque that points in a counterclockwise direction. So we choose this direction of torque created by force 1 to be positive, and these two torques created by these two forces to be negative because they point in the clockwise direction. Recall that because we have static equilibrium, because our entire arm is in static equilibrium, it's not moving, it's not translating or rotating, we can use the following equation. We can sum up all the torques acting on this bone, and that sum must be 0. So we choose torque 1 created by force 1 to be positive, so that means we have torque 1 minus torque 2 minus torque 3 is equal to 0. And we can rearrange this equation and we get torque 1 is equal to torque 2 plus torque 3. So once again, torque 1 is created by force 1, torque 2 is created by force 2, and torque 3 is created by force 3. Now recall that the torque of an the torque acting on an object is equal to the force multiplied by the lever arm, the distance or the perpendicular distance from the axis of rotation to where the force is acting. So we have torque 1 is equal to force 1 multiplied by L1, where L1 is simply 0.07 meters, equals force 2 L2 plus force 3 L3. So we simply rearrange our entire equation and solve for force 1, and we see force 1 is equal to F2 L2 plus F3 L3 divided by L1. So notice that F2 is simply the mass of the bones multiplied by the gravitational constant G. And F3 is simply the mass of the object multiplied by the gravitational constant G. So we know all these quantities, so that means we can solve for force 1. So force 1 is equal to 2.2 kilograms is the mass of the bones multiplied by the constant g 9.8 meters per second squared multiplied by L2. L2 is 0.2 meters because we take 20 centimeters and divide it by 100 to convert it to meters. Then we get plus 10 is the mass of our object, which is 10 kilograms, multiplied by the gravitational constant 9.8, multiplied by the lever arm L3, which is 0.4 meters, and divide that entire value by 0.07 meters. And we get approximately F1 is equal to 620 newtons. So this is the force required by the biceps muscle for our entire arm to be completely stationary, to exist in static equilibrium, meaning it's not rotating and it's not translating.